Sometimes in mathematics, a number appears again and again, not because we seek it, but because the universe keeps offering it.
Hi there everyone, good morning. So my name is Evangelina Tan and I'm from Citati West Campus Surabaya and I'm a grade 8. So today I'm becoming a magician. So now you might wonder, what is a magician exactly doing right here? Well, obviously we're going to do some math. So today's topic is about the Catalan numbers.
So, Catalan number is actually a type of sequence. It is from a natural numbers that have many applications in combinatorics, and they count as a number of ways in which it in a certain structure that can be formed by structures that often involve a balance or recursive arrangements.
Who discovered Catalan numbers?
As Europe flourished during the alignment of the advancing in literacy, math, and science, so too did the Leonhard Euler Brilliance, and he published over 800 works in his lifetime, and more than half of them were completed before he got blind. He was born in April 15, 1707 in Basel, Switzerland, to Pastor Paul and his wife Margareta. He spent his early years in a nearby village in Rehend, and by the age of 7, he was already studying an advanced algebra textbook far beyond the typical understanding of most children or even adults at that time. And at the age of 13, he's enrolled to the University of Basel, which is like many European universities, and admitted to the students much younger than is typical today.
Even though his university isn't that prestigious, but he was lucky that he can be taught by a mathematician, after all, and it's the greatest one.
Johann Bernoulli was one of the leading mathematicians that era, and by then the Isaac Newton is in his final years, and Gottfried Wilhelm has already passed away.
In 1751, Leonhard Euler asked,
"How many ways can I divide a polygon into triangles without any lines crossing?"
Nearly a century later, in the quiet of 1838, a Belgian mathematician saw the same pattern, but in a new disguise.
But then Eugene Charles Catalan asked,
"How many ways can you match parentheses so that every opening has a matching close and no confusion ever creeps in?"
And it turns out that this Belgian mathematician has made it a Catalan number which is named after himself and achieve a simple solution to the problem of enumerating the distinctions of the polygons by non-intersecting the diagonals into triangles in the 1838.
Okay, so now we're going to talk about one of the ways of the Catalan number, which is the dickpads, which can be shown what is in my hat today. Okay, so I see that we have a stack of cups right here. So let's see how many cups are there. 1, and then 2, 3, 4, 5, and 6. So before we continue on how are we going to solve these, so I'll give you guys the questions, obviously. How many ways are there to arrange these 6 cups? Remember the formula. Hi there, so welcome back. It's been quite a few minutes. Okay, so the answer is 132. For those of you who are correct, you're smart enough to do these questions. So this is the way, so it's C6 equals to 1 per 6 plus 1. C, 2 times 6, 6, which results 132 in the end. I'm pretty sure you know what is C meaning in right here. So yeah. Okay, let's start off with the formula. So remember that the Catalan number formula is equal to Cn, which is equal to 1 per n plus 1, C to n. Since we have 6 cups right here, right before, and we're gonna know how many are there the ways to second and second, so we're gonna input the n equals to 6 right here, which is 6 cups to be more specific. Okay, so now let's input the number, which is 6 right here. So C6 equals to 1 per 6 plus 1 times C 2 times 6, 6. So if we count it right here, it's 1 per 7 times 12 factorial, 6 factorial, 6 factorial. Okay, now let's solve it. 1 per 7 times 12 times 11 times 10 times 9 times 8 times 7 times 6 factorial so that we can cross it out. Okay, so now we're gonna put 6 factorial times 6 times 5 times 4 times 3 times 2 times 1. You can always put the 1 or not because that will still be the same thing. So let's cross these out. 6 factorial. Let's cross out the 7 with 7 so that we don't have to count it again later. And what we can cross again right here is the 6 with 2, which results 12 right here. And we can also do that for the 5. So with this one, it will result a 2, so it's with 10. 4 with 8, it will result 2 again. 3 with 9, it will result 3. So we can conclude it right here that it's gonna be 11 times 2 times 3 times 2, which equals to 11 times 2 is 22, right? And then 3 times 2 equals to 6, which results 132 in the end. So there are 132 patterns. Okay, get it? Okay, so how about a polygon triangulation? Let's say we have two four-sided polygon. This is a square right here. So how do we cut it into triangle? It's either we cut it this way, and we can reflect it and cut it the other way. Okay, so now you get it. So well, how many ways are there? Obviously, there are 2 ways. Okay, remember in your mind, there's 2 ways. So what about we have like a 5-sided one? Like for example, a pentagon. This is like the way. The first way is that we can do it this way. There will be triangles right here. Next one is that we can cut it another way, in which it will look like this. Next, it will be this way. And the next one would be and lastly, so how many ways are there? So there are 5 ways. So how do we make these triangles? It's just that we need the rotation from each of the sides. See, 1, 2, 3, 4, 5. Get it? So there are 5 ways. So what about a hexagon? So just remember the formula, because like if we kept on drawing this one by one, we won't be able to finish up a question. So if we use the Catalan number formula, let's say we have the hexagon one. So remember that's for a C4, because you have to minus the side by 2. So if we have C4 right here, it means that it's 1 per 4 plus 1, C2 times 4 and 4. So it means that it's 1 per 5, C8, 4. Originally, you know what I see right here. And 1 per 5, a factorial, 4 factorial, 4 factorial. Remember, here was the times up, so just use a dot. So it will result like a 14 in the end, okay? Okay, so now we're going to talk about a binary tree. So I'm sure you know what a binary tree. So we're going to talk about a binary tree right here. So we're going to draw this way. So maybe it's this one. But we have like a second one. So we're going to divide it this way. Even if you're or anything, it's still the same thing, just in one way. What about a 3 branch down? Okay, so a 3 way. Well, this is the way that we're supposed to draw it. Okay, so this one has one right here, and the next one would be we cut it out. This way, so there are only 2 ways. Okay, so what about the second formula down there? It's a bit long, but I'm pretty sure we'll make more sense again, so easy as we can. Okay, next one. So this is just a reflection of that. Okay, so lastly, it's a different, but it's still kind of the same thing. It's 4 branches. It looks like this way. Okay, so how many ways are there? Obviously, there are only 5 ways. So what about we have the 5 branches? Just use the formula and just remember it. And if you did remember it, you will have 14 in the end. Okay, get it. So lastly, this will be my question for you guys. So since I already told you about the cup singing using the Dick formula, so now I'm going to give you guys a question. Just answer it down below. It's pretty easy. Just use up the formula if you actually get it. With the rules of 3 up steps and 3 down steps. And never go below the x-axis. Okay? Answer down in the comment.